So today is very, I don't want to say it's very abstract, but it's not like 2 plus 2 is 4. Okay? It's not concrete math. You can see it, you can manipulate it, etc. Today's it's more conceptual today. It's more of a concept today that we're going to be working on and pushing ourselves through. Okay? So we are going to evaluate and graph some polynomial functions. On Monday, we started our polynomials unit with work with exponents. And today we're going to work with exponents again, but we're going to work with them in a different way than we did on Monday. Okay? Sorry, I should have scrolled down just a little bit so you could see the rest of my cartoon. Okay? Okay? So here we go. I forgot I gotta put the screen. Come on. Oh, SmartBoard is giving me fits today. Fits of fits. Yeah. So a polynomial is an expression with one variable. Okay? So in a polynomial, there will only be one variable. 9.76 times out of 10, that variable is going to be x. Okay? But it might not be. For instance, number 1 in your homework is not. Okay? Right? But most of the time, that variable is going to be x. And you're going to have different terms. Okay? You can this particular polynomial has 4 terms in it. Okay? Now, the only thing that you can do with a polynomial, just a polynomial, is you can simplify it or you can evaluate it. Meaning, you can say, what's the value of this polynomial if x were equal to 5? Then you plug 5 in, and you get your Now, that very same polynomial, if I write it in function notation, now it becomes a polynomial function. And a polynomial function is an equation. It's got the equal sign. Because it has the equal sign, now I can still simplify it. I can still evaluate it. But now I can also solve it. I can graph it. I can compare it to another polynomial function. I can do all of that stuff with it now that it's written in polynomial function. Okay? Notation. There is a difference. Expression versus equation. Simplify, evaluate. I could also say up here, we could we can add, subtract, multiply, and divide different polynomials. That's what you're going to do tomorrow, which reminds me again tomorrow. Bring your Chromebook and earbuds because you're going to watch a video and you're going to need to take notes on the video. So we got that going on. Now, with polynomials comes something called the standard form of a polynomial. Okay? And the standard form of a polynomial has the terms. Okay, remember, terms are separated by an addition or a subtraction symbol. It has the terms in descending order of exponents from left to right. So what I mean by that is you've got the biggest exponented term as your first one. Or if it's just an expression, you would just have your biggest exponented term. And then your next biggest, and then your next biggest, and then your next biggest, and all the way down until you have your constant term. And your constant term is just the number. Okay? So the number always just comes last. This biggest exponent here is called the degree of the polynomial. The degree of the polynomial tells you many, many wonderful things. Okay? And we'll get into that today, of all of the things that the degree of the polynomial tells you. Okay? Also, the number in front of this term is called the lead coefficient. And the lead coefficient will tell you some things too. We'll get into that. So that first term, that's the reason that we put that biggest exponented term first, because it gives us the lead coefficient and it gives us the degree right then and there. Okay? So let's take a moment here to reorganize this polynomial into standard form. Okay? So we would start here with f of x. What's our biggest exponented term? Negative 5x to the fourth. So that would come first. What's our next biggest exponent? Positive or negative? Positive. So that'll be plus 2x cubed. Next biggest one, Lucas? Negative x squared. Then just plus 4 at the end, because that's all that's left over, right? So that is standard form of our polynomial function. What is the degree? Or what is the lead coefficient? Negative 5. Okay. Now, like I said earlier, the degree will tell us a couple of different things. So the first thing that it's going to tell us is it's going to tell us the total solutions. It's also going to help us in determining what the graph or the end behavior or the picture, if you will, of the function. Now today, I am not looking for exact graphs. In this unit, I am not looking for exact graphs. I'm more looking for if you understand the pattern and you can easily just tell me, yep, this graph looks like this. Okay? Right? Exactness, we can always get the exactness by just plugging in some points, making a t-chart on some of these endpoints. Okay? So what we're going to do now is we're going to make ourselves a little chart, and we're going to see if we can see that pattern. So I'm going to give you a polynomial function. I'm going to tell you what the degree of that polynomial function is, and then I'm going to tell you the name of that polynomial function, or the type of that. And then I'm going to show you a picture of it too. Okay? So, for instance, f of x equals -6 has a degree of 0, and we call that a constant function. And that function is horizontal. It's a horizontal line. The value of that function is always the same, no matter what x you put in. The next function we dealt with last chapter, or last unit. It's a linear function. It's got a degree of 1. An example would be f of x equals 3x plus 2. The picture is a skew line. A skew line is a line that is not horizontal or vertical. Today of all days, the smart board decided to say, no, you know what, Lens? We've had it good for so long. I'm going to be goofy today. Next one is a quadratic function. It has a degree of 2 because 2 is the biggest exponent. F of x equals 5x squared plus x minus 4 is just one example. Excuse me. Anybody remember what those look like? Like you? Parabola? Could go upside down too, right? When what's negative? When the lead coefficient is negative. Yep. There we go. So it flip flop and it become a hump instead of u. Cubic function has a degree of 3. Kind of has that little wave going on through there. quartic function is next. It's got a degree of 4. I like to call it the warrior function, or the Wausau West function, because it makes a W. If it's a negative exponent, then it's a marathon function. It makes an M. I don't like that. Degree of 5 would be a quintic function. Would be like f of x equals, we'll say 3x to the 5th minus, I don't know, 2x cubed plus x squared minus x plus 1. Okay. That one's going to look like this. It's going to have 2 camel humps. Based off of those first few functions, does anybody notice a pattern? Pete? They go opposite. So the sides, the left and the right sides, go in the same direction when they're even. When they're odd, they go in the opposite direction. And you guys, I think, have seen that before in probably in algebra 2-ish. Something like that. Okay? So when we get into graphing these functions, like we're going to do here, and talking about end behavior, let me get a shade going on here. Let's see, it's Wednesday, so we want the pink shade. Okay? So what I'm most concerned about with these functions is something called end behavior. And the end behavior of a function is what that function is doing and we start with function. What that function is doing on the right and on the left side of the graph. On the right, that's when x is going to positive infinity. Okay? It would be like what the value of your function is if you were able to plug in positive infinity. On the left, it's as if it's going to negative infinity. Now, the wordage of how to do that is very important. I'm sure you guys after this. You guys want to watch the video. Pick up the video. You can pick up the video from 19 minutes. Okay. So on these next 4 examples, what I want you to do is I need you to do, I should say. What I need you to do is I need you to write down what the function is, draw a picture of the graph, and then write down the wordage underneath as is. Because that's the wordage that I'm talking about that needs to be written in that specific way. So I'm going to give you a minute or two to copy this part of the slide down in your notes so that we can just talk about it. All right. So what I'm asking here is I'm asking, so the end behavior. So as x approaches positive infinity, that's saying the right side of my graph. Okay? Where is my function headed? And I got three choices to where it's headed. It's either headed straight up, and we would call that it's heading towards positive infinity. It could be headed straight down if it's headed to negative infinity. Or later on, and this is more when we get into rational functions in December, it could be headed out to a number. Okay? It could be approaching a number that is headed up that way. Okay? So in this particular case, and we're always going to assume that we see all of the twists and the curves and there's no other things going on. So we're going to assume that this is going to continue to head straight up, so this function would be headed towards positive infinity. Okay? Now, as written here, that's how I need it written if you have to produce it. For instance, on like numbers 1 through 6 on your homework, where it says simplify it, which means put it in standard form, and then state the end behavior. So you would say, as x approaches positive infinity, f of x approaches positive infinity in this particular case. The other side, the left side, as x is going to negative infinity, my function is headed down, so that means it's going to negative infinity there. Okay? Now, the difference between 1 and 2, they're both an odd degree, but the difference is number 2 has a negative lead coefficient. Okay? So notice how that changes, and that the right side of my graph now is headed downstairs, and the left side of my graph is going up to on high. Okay? Same thing on this next slide. Give you a couple of minutes here to copy down function, picture, and behavior. And you can fill in the end behavior also. So now we have an even degree. So as we had said before, the sides should be going in the same direction. So here on example number 3, the right side is going up, the left side is going up, so they are both going to positive infinity. Yeah? And again, that verbiage is the same. If you'll notice the verbiage, it's like a point. A point is x comma y, and this is as x, whatever x does, comma, whatever y does, because f of x is synonymous with y in function notation. So think of it as a point. Negative lead coefficient, once again, notice how they both now go down. Okay? So, to summarize it, once again, I would never ask you for an exact graph of these things. Okay? I would ask you only for a sketch. Okay? But what I will ask you for is the end behavior. And you don't need the graph to tell you the end behavior. Is it easier? Yes, by all means, it's easier to look at the picture and say, oh, the right side's going up, left side's going down, or vice versa, or going in the same direction. Yes, that is 100% easier. But that's why I give you those tools so you could make yourself those graphs or those sketches. Okay? So the first question that you should ask yourself is the highest power of these functions odd or even? You know, there we go. Okay? If they are odd, or if the degree is odd, then the sides go in opposite directions. If the degree is even, then they go in the same direction. The second question that you have to ask yourself is, what is the positivity of the lead coefficient? Because if the lead coefficient is positive, then the right side will always go up. And then depending upon the odd or evenness of the degree, that will determine the left side. If it's even, the left side will also go up. If it's odd, the left side will go down. If your lead coefficient is negative, then your right side will go down. And again, based upon the degree, that will determine what the left side is. Okay? The phrase, as x approaches positive infinity, that means the right side of your graph. And as x approaches negative infinity, that is going to mean the left side of your graph. That's all that means. So the first question, or the first statement you give me for end behavior, is what the right side of your graph is doing, and then the next one is what the left side. You still got room for one more. Yeah. So, what I would like you to do now is, given that function, I would like you to, 1, put it in standard form. 2, give me an appropriate sketch to go along with it. And 3, state the end behavior. Okay? So it's a 3-part question. Negative 2x to the 7th minus 15x to the 4th plus 3x cubed minus x minus 12. Yes? Okay. All right. That's got an odd degree. So the sides are going to go in opposite directions. And it's got a negative leading coefficient. So it's going to start up to the left. And end down that way. 1, 2, 3, 4, 5, 6. Yep. 3 sets of humps. Yes, sir. Yep. Biggest exponent. Yep. Biggest exponent, which should be your first term, and then leading coefficient should be that very first number. Okay. So my end behavior would be, as x approaches positive infinity, my function is going to negative infinity. And as x approaches negative infinity, my function is going to positive infinity. Last comment that I will make, for some reason, after today, for some people, they get the order of that flipped around. And so I'll get some really funky answers. I'll get like, as f of x goes to positive infinity, f of x goes to negative infinity. And I'm like, that doesn't make any kind of sense. Okay? X is first, y is second. Okay? Okay? That's all I got for you today. You can now, numbers 1 through 6 on your homework. The first part says simplify, and then you should, from now on, you should also be giving your answers in standard form. So you should be stating all of your polynomials for the rest of the year in standard form. Okay? All right? And then it says, give me the end behavior for all 6 of them.